All right. Uh, let's live. Well, welcome back to Google Centers. I'm Aldi Brastio, the founder and the author, and the 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 only one. All right. I just come back here and want to try to live streaming here on YouTube to share you guys about aerospace, about aeronautics, airplane, or something like that, or 3D model, CATI, ANSYS, and so on. And now I just wanna, yeah, give you uh, explanations about converging airflow, converging cone, and Bernoulli principle or Bernoulli theorem, and maybe this diverging cone on the airflow through the diverging cone like that, and the last one I have a paradox that they like an aerodynamic paradox, right? Um, yeah, the first one I just wanna talk about the aerodynamics or airflow through a converging cone. Sorry, that. Wait, I have to set this first because wait a minute. Okay. Uh-huh. Wait, I have to check this one first. Right. First, I have many mistake here because this is my first time to going to live. Okay. So I just we effort to a converging cone. I have a like a example for you. It's when the cars on crowded highway reach a point where the highway narrows, one of the two things will happen. The first one is maybe the cars upstream will have to slow down, right? Or the second one is the cars past the point of constriction will have to speed up, right? Possibly both that examples will happen. In any case, the cars downstream will travel faster than the cars upstream, but obviously the number of cars will remain the same, right? A similar condition exists when airflow through a converging cone, as shown in this figure. I will show you this figure, right? And a similar condition exists that airflow through a converging cone, like this figure. Uh, the air volume or Q, we call Q this uh, equals to A times V, where the Q are air volume in CFM, and the A is the area in square feet, and V is the average velocity in feet per minute. Right. Um, as the airflow passes through the converging cone, the airflow luminance, then GFM obviously will remain the same ahead and past the converging cone. This can be expressed like Q1 equals to Q2, right? And maybe you can rewrite and substitute that Q is equal to A times V, then substitute to Q1 equals to Q2, and just change the subscription, and will be the equation will be A1 times V2. I'm sorry, A1 times V1 equals to A2 times V2, right there. After we know about the uh, simple example of the converging cone like that. We have to know about the Bernoulli principle of continuity, right? This simple obvious equation is called principle of continuity. Because of air's volume, CFM continues to be the same before or after the point constriction as the air passes through the converging cone. It will accelerate from V1 to larger air velocity V2 because the area A2 is smaller than the area A1, right? You can see in that picture on the airflow to a converging cone uh, like this, right? And I want to show you an example with the uh, mathematical problems like this. I will show you. All right, wait a minute. Right, this example. Let's can assume that the upstream duct like a 24 inch, so A1 is equal to 3.14 feet square. Next, let's assume that the downstream duct it's 18 inch, and so A2 becomes 1.767 feet square. If the Q equals to 8,155 CFM, we get the P1 is uh, Q1 divided by A1. Then we have result here. It's 2,119 FPM, and the VP1 zero point 0.5 inch water column. WC is water column here, right? And V2 is equal to Q divided by A2, right? It's this has result 5,000 uh, 011 PM, and VBU2 it's equal to 1.57 in water column, right? And this substantial increase in velocity pressure from 0.5 to 1.57 in water column, of course, will result in increased kinetic energy, right? Which will be obtained at the expense of decreased static pressure. Basically, this is the Bernoulli theorem, which in its simple form say when the air velocity increase, right? Air velocity increase, the static pressure will decrease. Okay, just remember that. While the velocity increase, the static pressure decrease, right? And uh, this is the easy to understand, right? But the relation is always says when the air velocity decrease as a diverging cone, we talk after this, alright? The static pressure will increase. This increase is called static region. This is more difficult to understand. It will maybe be discussed in more detail in section of this diverging cone after this slide. A converging cone passive fan is often used to increase the air penetration for such application as shows blowing or comfort cooling maybe. A converging cone pass the scroll housing and centrifugal fan usually works without any problem, right? Can has to be taken. However, on the converging cone pass an axial flow fan because there often is air spin pass axial flow fan even if it is a financial fan with guide fins and that are supposed to remove the air spin. If a little air spin remains past the fan, it is multiplied manifold as air travel to a smaller diameter because it tends to retain its circumferential component like that. As a result, at the smaller diameter, the revolutions per minute of the air spin become considerably larger. Just like a watch chain spun around a finger turn faster and faster and faster as the chains become shorter like that. Here is, yeah, here I will show you the illustrating phenomenon that uh, I just found. Wait, I will hide this one, and show this. All right. Wait, maybe you can see this. I will, yeah, this. All right. All right. This is the illustration that I found in the book that I just forgot the book. All right. Sorry, I just forgot the book and I just take a picture of this and take a screenshot and explain to you about this. You know, here the example is showing the phenomenon that the airspeed increases as the converging cone becomes smaller. Uh, I just remember about back in 1949, the designer tested for like this one, a 40-inch fan axial fan with a 12-inch half diameter, resulting is an unusual large half dip ratio of 86%, right? This was done because the requirements were for a small airflow in CFM and a high static pressure. A static fan would have been a better selection, but the customer instead the fan axle fan, right? Since the annular area was so small, right? I used the designer, sorry, not me. The designer used a 6-inch test duct past the unit in order to get good air velocity to the duct was a transition cone from 40-inch down to 6-inch, as shown in that figure, right? And this setup of course was not accordance with the Air Movement and Control Association or AMCA test code, which required that the test duct area be within 5%, just 5% of the fan outlet area. A better test would have been on a nozzle chamber instead of a test duct, but in 1949, very few companies had a nozzle chamber. To my surprise, I found zero air velocity in the 6-inch test duct. The reason was the remaining air spin past the fan became so strong in transition cone. The, the friction path became excessive and used up all the static pressure available. After I put two longitudinal, after the designer put the two longitudinal cross sheet in the transition cone to prevent the air spin, the proper air flow was restored and fairly normal duct test could be run like that. That's the illustration I just found. And yeah, so wait a minute. All right. This. All right. After that, after we know the thermal theorem and converging airflow partial converging cone, we have to know about the airflow to a diverging cone, right? The first one I have to show you about these illustrations. Converging, sorry, divergent illustration. To this, right? Wait, I have to do this, right? This one, right? This one, the divergent system, the illustration of divergent system. As discussed earlier, a converging cone as shown in figure 1.7 or the figure of the converging system will produce an increased velocity past the cone, resulting in increased kinetic energy, which is obtained at the expense of decreased static pressure, right? By the same token, a diverging cone as shown in this figure, will produce a decreased air velocity past the cone, resulting in a decreased kinetic energy. And the question is, will this difference in kinetic energy be lost? Will it be or not? Yeah, about half of it will be lost, right? The answer is mainly due to turbulence. The other half, believe it or not, will be regained by an increased static pressure as stated by Bernoulli theorem, provided that the cone angle is small, about 7 degrees or um, less on one side is recommended, while air normally flow from higher static pressure to lower static pressure. Yeah, right. Here is a case where the opposite takes place. Air is flowing from lower static pressure to higher static pressure, right? Using the same dimension, uh, the same airflow as in figure on the before on the converging example with a number. The velocity pressure now will decrease from 1.57 to 0.50 in water column, right? For reduction of 1.07 in water column, one half of this, or about 0.53 in water column, can be expected as static regain, right? Such regain is sometimes obtained by the use of the diffusion power cell fan. After we know about that converging, diverging, and Bernoulli theorem, I have to show you, and I just uh, read this, this paradox, the paradox, maybe 2 weeks ago or 1 week ago. Sorry, just for the maybe 2 weeks. I wrote about aerodynamic paradox. It's normally as we go along with airflow to the duct system, the static pressure is highest upstream and gradually decrease from there, right? All right, this one I have to show you. This. All right, I have to doing this, okay? And this is the example or illustration the aerodynamic paradox. Yeah, this is the reason why the airflow, the high static pressure upstream force the air to the filters and the others. Therefore, it seems hard to believe that the static pressure will increase as air passes through the diverging cone. It seems contrary to common sense. It seems paradoxical, right? Let us discuss a device that might convince you the truth of the preceding statement. This is this device, right? This is the illustration. It's called aerodynamic paradox, right? Shown in this figure. It consists of a silver plate A with a pipe B on top, another thin like white weight. This is suspended about a half in the below A in such a way that it can easily move up and move up. Alright. If we blow into the pipe on the top, we would expect that the air stream will blow the lower disc down. Actually, the lower disc will um, move up, but let me explain why. The air stream leaving the pipe will turn 19 degrees and move outward since it has no other way to go. As it moves outward, the cross-sectional area becomes larger, as in a diverging cone, right? So the air velocity becomes smaller as the airstream reaches the outside of the disc. The air velocity will be quite small, and the static pressure at that point will be close to the atmospheric pressure of the surrounding environment, right? Uh, For the inside, however, where the cross-sectional area is much smaller, the velocity of the air flowing outward is larger, and per Bernoulli, the static pressure therefore is lower than the atmospheric pressure that pushes again the underside of the lower disc. As a result, that yeah As a result, the lower disc is lifted up against the upper plate. The moment the lower disc touches the upper plate, the airstream is stalled and the lower disc will drop again. That yeah phenomenon that will repeat itself, repeat and repeat, repeat. That's we call about aerodynamics paradox. Yeah, that's all about the uh, aero aerodynamic paradox, divergent, and about theorem. This this is the yes, it's so much, so many explanation here, and here. Yeah, just I just wanna say that maybe I have to end this. How is it? End this live stream on the reason maybe next I'm gonna live again to you guys and yeah, just see you and just don't follow, I'm sorry. Don't forget to subscribe and yeah, like and comment if you have any questions. Just drop down below in comment or just DM me on Insta or email me, just whatever you want. Yeah, if you have any questions, right? And yeah, see you.